Hi BC Cal students, this video is for the mixed review for sequences and series. I've been having some trouble with the YouTube app doing this weird zoom thing on my videos. This is why this is already written on. I already had done some work and I don't want to print another 20-page copy. So we're going to just get started with number 5 and ignoring that I wrote this information over here. We'll just cross this out. We have this series an, which is -1 to the n divided by the square root of n plus -1 to the n. We'll write that over here. So we have the series from n equals 1 to infinity of -1 to the nth power divided by the square root of n plus -1 to the n power. We are going through these three options. So the series is alternating because we have -1 to a power that can be even or odd. So that will make the terms alternate in sign. For 2, what this means is every term, the rightmost term in the series is the smallest term in the series at some point. And that's not going to be true. We can write down 4 terms to see what happens. If n equals 2, we have -1 squared, which is 1 over the square root of n plus 1. If n equals 3, we have -1 over the square root of n minus 1. If n equals 4, we get 1 over the square root of n plus 1. And if n equals 5, we have -1 over the square root of n minus 1. So the terms, they do alternate in sign, but they don't necessarily decrease in magnitude. As fractions work, the larger the denominator, if the two fractions have the same numerator, the fraction with the larger denominator is the smaller fraction. So this fraction for 2 is less than this fraction for 3. For n equals 3, but in absolute value, since these would all then just be +1, we would end up with sometimes an plus 1 is less than an, and sometimes an is less than an plus 1. So these don't always decrease in magnitude. For 3, the limit, so regardless of having 1 over the square root of n plus 1 or -1 over the square root of n minus 1, the limit is going to be 0. So both 1 and 3 hold up. So the answer here is D. We omitted 6, 7, and 8, and so we're going to get on to number 9. And for number 9, we have, why did some of these papers print blank? So for number 9, we have -1 to the n divided by the cube root of n. And we can just write this as n to the 1/3 instead. And so we are trying to see if the series converges conditionally. Absolutely, the series converges, but neither conditionally nor absolutely, or the series diverges. So we need to check the do the alternating series test. And for the alternating series test, we would have, do the terms alternate in sign? That's clearly going to be true because, again, we have -1 to a power that can be even or odd. For 2, the terms decrease in magnitude because if we ignore the -1, we just have 1 over the cube root of n. And so as n gets larger, we're going to be dividing by a progressively larger number. So they do decrease in magnitude. And 3, the limit for this sequence is 0. So the 3 conditions for the alternating series test are met. And when that happens, the 3 together imply at least conditional convergence. So C and D are out. And so now we go for absolute convergence. And for absolute convergence, you are looking at the series without the -1. So if we have -1 to the, I said ignore the -1 and wrote it anyway. We have 1 over n to the 1/3. And we know by the P series, this is a divergent series. So the series is not absolutely convergent. It is only conditionally convergent. For number 10, we have another set of alternating series. For A, the terms, all of these are going to decrease in magnitude because, all of these are going to alternate signs because they're all alternating series. So the first condition is met. The easiest way to check all of these is look at the limit. So the limit for A is the limit when n goes to infinity of 1 minus n over n. And remember, when the degree of the numerator is equal to the degree of the denominator, the limit is the ratio of the leading coefficients. So this limit is -1. For the alternating series, the limit has to be 0. So A doesn't work. For B, the limit when n tends to infinity is going to be 1/2 because we have n to the first divided by 2n. So this limit equals, we're just going to put in some quotation marks. That limit equals 1/2. For C, you could rewrite this as n. So n squared divided by the square root of n is n to the 3/2 over 3. When you go to infinity, the limit is going to be infinity. So it's going to be divergent anyway. So C doesn't work. And so by process of elimination, we get D to be correct. You could rewrite this as 2 over the square root of n. And the terms decrease in magnitude, they alternate sign, and the limit of the sequence is 0. So that's going to be conditionally convergent. It would not be absolutely convergent because you would end up with P equals 1/2. For number 11, we have another set of alternating series. For A, we just saw that anything over the square root of n would be a number over the square root of n would be a conditionally convergent alternating series. So A can't be correct because this should be converges by the alternating series test. For B, if we look at the limit when n goes to infinity, we can ignore the 2 because it does not have a variable. So we would have 4 square root n divided by square root n. And when n tends to infinity, that limit is going to be 4. So B is also not correct. For C, and so C requires some trickery. If we look at n, ignore the -1 to the n plus 1 for a moment. If you look at n equals, so we're going to have n equals 1, you would have the cosine of pi. For n equals 2, you get the cosine of 2 pi. For n equals 3, you would have cosine 3 pi. And so then the cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1. This is the same as having -1 to the n power. So now if we can replace cosine n pi with -1 to the n power, then we could rewrite this as -1 to the n plus 1 times -1 to the n. That's going to be -1 to the 2n plus 1 over n squared. So if -1, 2n plus 1 is always odd. So if you have -1 always to an odd power, the terms don't alternate in sign. So we would end up with, even though the other two parts of the alternating series test work out, the fact that they don't alternate signs mean you can't use the alternating series test. And so by process of elimination, D is going to be correct. Did we do number 12? Yeah. So number 12, which of the following is a convergent P series? Well, A isn't because it's not a fraction. B is a geometric series. C is not because P equals 1/2. And if we rewrote D, that is just 1 over n to the 3/2. It's the square root of n cubed. So D is a convergent P series. So we're going to ignore anything that has limit comparison. So 13 was out. So 13 was out. 14 was out. Was 15 out? Yep, because it's a direct comparison. 16 All right, let's do 16. So which of the following series are conditionally convergent? So we've seen this -1 over the square root of n a couple of times. So we know 2 is conditionally convergent. 2 is conditionally convergent. So that means that we can eliminate a. I guess a is the only one we can eliminate. For 3, we have -1 to the n over n plus 2. So we haven't talked about direct comparison or limit comparison, but you can compare this to -1 over n, which is also conditionally convergent. So 3 is going to be conditionally convergent as well. And then this is going to be absolutely convergent because, in fact, in absolute value, so it's going to be conditionally convergent because the terms alternating sign, they decrease in magnitude, and the limit for the sequence is 0. But in absolute value, you would have 1 over n factorial, which is clearly convergent. If we did the ratio test, this limit is going to be less than 1. So this is absolutely convergent, and we're looking for only conditionally convergent. So that's going to mean that 2 and 3 are the answer. I would put the stronger wording here should be only conditionally convergent, because all absolutely convergent series are conditionally convergent, but because they pass alternating series test. Did we do 17? No, that's direct comparison. For what values of p would this converge? I think we can do 18. So for 18, we should do the let's do the ratio test so we can see what happens. We would have the limit when n goes to infinity of n plus 1 to the p power over 4 to the n plus 1, and then we divide by the an term or multiply by the reciprocal, so we have 4 to the n over n to the p power. So what we end up with in a rewrite is the limit when n goes to infinity, that's a terrible infinity, of n plus 1 to the p over n to the p times. So 4 to the n over 4 to the n plus 1 is just 1 over 4. So if you expand this out, you're going to have n to the p over n to the p, and that limit is 1. And so times a fourth, this is always going to be less than 1. So this will converge for any value of p that is greater than 0. So A is the correct answer. Convergent for any value of p that is greater than 0. Consider this sequence. This is a limit comparison. So 19 is out. Which of the following series converge? We can do 20. All right, so 1 converges because p equals 2. 2 does not converge because p equals 1. And 3 converges because, again, it's an alternating series. This is conditionally convergent. So 1 and 3 are our answers that converge, and that's going to be D. 21 we skipped because it's a direct comparison. 22 I think we dropped out. I don't know why that printed. 23 we did not do because we haven't done power series. 24 I think we can do 24. So this is 1 over n to the 3/2 power. So this is a convergent p series. So 1 converges. 2 is 1 over 3 to the n power, which is a convergent geometric series. So that converges. And 3. So imagine you had the integral from 1 to infinity. Now, we have the integral from 1 to infinity of 1 over n ln n. So we can just say that's 1 over x ln x. And if we did some u substitution, u would equal to ln of x, and du would equal 1 over x dx. So we end up with the ln of x. evaluated from 1 to infinity. Now, a couple problems with this are, one, that if n is 1, then you end up with 0 in the denominator. So you can't actually work this out. But even if you took this from 2 to infinity, you end up with the ln of 2, the ln of the ln of 2 out to infinity. This slowly goes to infinity. And so this integral is divergent. And for the integral test, if the integral diverges, the series that represents the integral also diverges. So 3 is not convergent. So our answer is only 1 and 2. 25 was a direct comparison or limit comparison, so we skipped that one for right now. I think that leaves us with 26 was a limit comparison, so we take that out. 27, which of the following series are conditionally convergent? 1 is the harmonic series if we ignore the negative one, so it's conditionally convergent because alternating series test works on this one. Alternating series test. This one is absolutely convergent. Now, again, the wording should be only conditionally convergent. This one is, the 2 is absolutely convergent because it passes alternating series test. And if you ignore the negative one, you have 1 over n cubed, which is going to mean p equals 3. So that's convergent. And again, we see the negative 1 to the n over square root n, which is another conditionally convergent. So 1 and 3 only. For 28, I think that's the last one. If the ratio test is applied, if the ratio test is applied to the series, blah, 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 which of the following inequalities results implying that the series converges? Let's find out. So ratio test, we'll write this over here, get some room. We're going to just ignore the options and see what work we get. So we have the limit when n goes to infinity of n plus 1 times pi to the 2 times n plus 1 over 17 to the n plus 1. And then we multiply by the reciprocal. So 17 to the n over n times 17 to the n over n times pi to the 2n power. So what happens is 17 to the n over 17 to the n plus 1 we get, and all of this in absolute value should be less than 1. So we get the limit when n tends to infinity. So n plus 1, we're going to rewrite this as n plus 1 over n times 1 over 17. And then pi to the 2n plus 1 is pi to the 2n plus 2. So 2n plus 2, so pi to the 2n plus 2 divided by pi to the 2n is going to leave us with pi squared in the numerator. So let's see what our answer choices are. So we need, let's see, 17, nope. We need a 17n in the denominator, n plus 1. Yeah, so B is going to be our answer. Nope, A is our answer. So we end up with 17n, not 17 to the n. So we had pi to the 2n. So if we substitute in n plus 1, we get 2n plus 2. Divide these out, you get pi squared. B is the answer, but I feel like a pi squared is missing. So we should have 1. Oh, I'm sorry. C is the answer. I'm looking right at it. It's n plus 1 pi squared over 17n. So C is the correct answer. Excuse me. All right. So that concludes this video for the multiple choice part of the mixed review for sequences and series. I will have a video for the free response part later on today. The Zoom thing on YouTube is messing up all my videos. Talk to you guys later.